Module 3, Scaling and Updating Applications. Scaling applications in Kubernetes. Kubernetes provides powerful tools for scaling applications horizontally and vertically. Horizontal scaling involves adding more instances of an application to handle increased load, while vertical scaling involves increasing the resources available to each instance of the application. Here are some of the ways to scale applications in Kubernetes. 1. Manual scaling. You can manually scale a deployment or replica set by running the kubectl scale command and specifying the desired number of replicas. For example, to scale a deployment named myapp to 3 replicas, you can run kubectl scale replicas equals 3 deployment/myapp. 2. Automatic scaling. You can use Kubernetes Horizontal Pod Autoscaler, HPA, to automatically scale a deployment based on CPU or memory usage. The HPA monitors the resource utilization of the pods in the deployment and adjusts the number of replicas to maintain a target utilization level. 3. Cluster-level scaling. You can scale your entire cluster by adding or removing nodes. Kubernetes supports various node scaling strategies, including manual scaling, automatic scaling based on resource usage, and cloud provider-specific scaling mechanisms. In summary, scaling applications in Kubernetes involves manual or automatic scaling of deployments, horizontal scaling using the HPA, cluster-level scaling, vertical scaling using the VPA, and rolling updates. Kubernetes provides a powerful and flexible platform for scaling containerized applications, making it easy to handle increased traffic and load. Updating applications with rolling updates and rollbacks. Kubernetes supports rolling updates and rollbacks to update and revert changes to applications running in the cluster. Rolling updates allow you to update an application gradually, one pod at a time, while keeping the application running. Kubernetes will replace the old pods with new ones, verifying that each new pod is healthy before moving on to the next one. This approach ensures that your application is always available during the update process. In summary, rolling updates and rollbacks are essential features of Kubernetes that allow you to update and revert changes to applications running in the cluster. Rolling updates ensure that your application is always available during the update process, while rollbacks provide a safety net in case of issues with the new version. Implementing readiness and liveness probes. Readiness and liveness probes are essential features in Kubernetes that allow you to check the health and availability of your application running in the cluster. A readiness probe checks whether your application is ready to receive traffic, while a liveness probe checks whether your application is still running. Here are the general steps to implement readiness and liveness probes in Kubernetes. 1. Define the probes. You can define the probes by writing a YAML file that describes the probe's properties, including the type of probe, the path to the endpoint to check, and the expected response. You can also configure other properties such as the probe's initial delay, timeout, and period. 2. Add the probes to your pod spec. You can add the probes to your pod spec by including the YAML file that defines the probes. You can define multiple probes in the same file and configure them for different containers in your pod. 3. Monitor the probes. Kubernetes will automatically monitor the probes and update the pod status based on their results. If a probe fails, Kubernetes will mark the pod as unhealthy and either restart the container or stop sending traffic to it, depending on the probe's configuration. 4. Use the probes and service endpoints. You can use the probes and service endpoints to ensure that traffic is only sent to healthy pods. Kubernetes will automatically route traffic to healthy pods and avoid sending traffic to pods that are failing the probes. In summary, implementing readiness and liveness probes in Kubernetes involves defining the probes, adding them to your pod spec, monitoring the probes, and using them in service endpoints. By using readiness and liveness probes, you can ensure that your application is always available and healthy, making it easier to manage and scale containerized applications. Module 4, Storage and Networking. Storage in Kubernetes. Storage is an essential component of containerized applications, and Kubernetes provides a flexible and scalable platform for managing storage for containerized applications. There are several types of storage options available in Kubernetes, including 1. Volumes. Volumes are the simplest storage option in Kubernetes, and they provide a way to store data that needs to be shared between containers in a pod. Volumes can be backed by various storage systems, including local storage, network file systems, and cloud storage providers. 2. Persistent volumes. PVs provide a way to manage network-attached storage, NAS, or block storage that can be used by multiple pods. PVs can be manually provisioned by a cluster administrator or dynamically provisioned by storage classes defined in the cluster. 3. Persistent volume claims. PVCs are requests for a specific amount and type of storage that can be used by a pod. When a PVC is created, Kubernetes automatically provisions a matching PV, or it can bind to an existing PV that satisfies the claim's requirements. 4. Stateful sets. Stateful sets are a way to manage stateful applications that require persistent storage. Stateful sets ensure that each pod in the set has a unique and stable identity, and they manage the creation and deletion of PVCs and PVs. In summary, Kubernetes provides a flexible and scalable platform for managing storage for containerized applications. Storage options in Kubernetes include volumes, persistent volume claims, stateful sets, and dynamic provisioning. By using these storage options, you can ensure that your containerized applications have access to the storage resources they need to store data reliably and efficiently. Network models in Kubernetes. Kubernetes provides a flexible and scalable networking model for containerized applications that allows containers to communicate with each other and with the outside world. Some of the common Kubernetes networking plugins are: 1. Flannel. Flannel is a popular networking plugin that provides a simple and lightweight way to network Kubernetes pods across multiple hosts. Flannel creates an overlay network that allows pods to communicate with each other using standard IP networking. 2. Calico. Calico is a networking plugin that provides advanced networking features, including network policy enforcement and encryption. Calico uses a distributed architecture to provide high performance and scalability. 3. Cilium. Cilium is a networking plugin that provides advanced networking features, including network security, load balancing, and service discovery. Cilium uses a combination of kernel-level networking and BPF, Berkeley Packet Filter, technology to provide high performance and scalability. In summary, Kubernetes provides a flexible and scalable networking model for containerized applications, with container-to-container and pod-to-pod networking. Kubernetes also provides several networking plugins that allow communication between pods running on different nodes, as well as communication with external services and resources. By using these networking options, you can ensure that your containerized applications have reliable and efficient communication channels, making them easier to manage and scale. Service discovery and load balancing. Service discovery and load balancing are critical components of Kubernetes networking that allow containerized applications to be easily accessed and scaled. In Kubernetes, a service is an abstraction layer that defines a logical set of pods and a policy for accessing them. Services provide a stable IP address and DNS name for a set of pods, allowing other pods and external clients to access the service without needing to know the details of the underlying pod IP addresses. Kubernetes provides several types of services, including: 1. Cluster IP. Cluster IP services provide a virtual IP address that is only accessible from within the cluster. This type of service is commonly used for internal communication between pods. 2. Node port. Node port services provide a static port on each node in the cluster, allowing the service to be accessed from outside the cluster using the node's IP address. 3. Load balancer. Load balancer services provide a public IP address that can be used to load balance traffic across multiple pods. This type of service is commonly used for external-facing services that require high availability and scalability. 4. External name. External name services provide a DNS name that points to an external service outside the cluster, allowing pods to access external resources as if they were internal services. In summary, service discovery and load balancing are critical components of Kubernetes networking that allow containerized applications to be easily accessed and scaled. Kubernetes provides several types of services, including cluster IP, node port, load balancer, and external name, as well as built-in load balancing support. By using these networking options, you can ensure that your containerized applications have reliable and efficient access to the services they need to function correctly. Thanks for watching. For more information, like, comment, and subscribe our channel.